Welcome back to our discussion on magnetic effect of electric current. In this segment, we are going to discuss about the magnetic field due to a current through a straight conductor, a circular loop, a solenoid, Maxwell's right-hand thumb rule, and the applications of electromagnet. When the current flows through the conductor, the magnetic needle placed near it shows deflection, indicating the presence of magnetic field due to the flow of current. Let's conduct a small activity to know the direction of the magnetic field due to the change in the direction of the current in a straight conductor. Place a straight copper wire parallel to and over a compass needle. If the current is allowed to flow from north to south, the north pole of the compass needle would move towards the east. If we replace the terminals of the battery in the circuit, which results in the change in the direction of the current through the copper wire, that is from south to north, we now observe the movement of the needle in the opposite direction, that is towards the west, which means the direction of the magnetic field becomes opposite when the direction of the current is reversed. Let's conduct another activity to determine the pattern of the magnetic field due to a current through a straight conductor. First, insert a thick copper wire through the center normal to the plane of a rectangular cardboard. Connect the copper wire vertically between the points X and Y. Connect it in series with a battery, a plug key, a variable resistance and an ammeter. Allow the current to flow through it and gently tap the cardboard. We observe the iron filings align themselves in a pattern of concentric circles around the copper wire. These concentric circles represent the magnetic field lines around a straight current carrying conductor. The direction of the field lines could be found by placing a compass at a point, say P, over a circle. The direction of the north pole of the compass needle would give the direction of the field lines produced by the electric current through the straight wire at the point P. We also observe the direction of the magnetic field lines get reversed if the direction of the current through the straight copper wire is reversed. If we vary the current in the circuit using the rheostat, the deflection of the needle changes. In fact, if the current is increased, the deflection also increases. And if the current is decreased, the deflection of the needle decreases. It indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases and decreases as the current decreases. For the same current, if the compass is moved away from the copper wire, we observe the deflection in the needle decreases. Thus, the magnetic field produced by a given current in the conductor decreases as the distances from it increases. This is observed from the figure by the larger concentric circles representing the magnetic field around a current carrying straight conductor becoming larger and larger as we move away from it. The most convenient way of finding the direction of the magnetic field in a current carrying straight conductor is given by Maxwell's right-hand thumb rule. Imagine holding a current carrying straight conductor in a right hand such that the thumb points towards the direction of the current and the fingers wrapping around the conductor shows the direction of the magnetic field lines. Maxwell's right-hand thumb rule could also be applied to a coil of wire carrying current to find the direction of the magnetic field. A current through a horizontal power line flows in east to west direction. Applying right-hand thumb rule, the magnetic field at any point below or above the wire turns clockwise in a plane perpendicular to the wire when viewed from the east end and anti-clockwise when viewed from the west end. Now we are going to discuss about the magnetic field lines due to a current through a circular loop. If suppose a straight wire is bent in the form of a circular loop and current is passed through it, how would the magnetic field lines look like? Well, similar to the pattern of the magnetic field lines around a current carrying straight conductor, at every point of a current carrying circular loop, the magnetic field lines are in the pattern of concentric circles which would become larger and larger as we move away from the wire, since the magnetic field depends inversely on the distance. At the center of the circular loop, the arcs of the big circles would appear as straight lines. Now let's observe the magnetic field lines around a circular coil of wire. A circular coil of wire having large number of turns is inserted into the two holes of the cardboard. The ends of the coil is connected to a battery. Sprinkle some iron filings and plug the key and gently tap the board. The iron filings align themselves in the pattern of concentric circles at the 2 points representing magnetic field lines. Maxwell's right-hand thumb rule is used to find the direction of the current even in the circular coil of wire. If the direction of the current is in the anti-clockwise direction, at every point on the circular coil, we visualize the direction of the magnetic field in this manner. Every point on the wire carrying current would give rise to the magnetic field appearing as straight lines at the center of the loop. Applying right-hand thumb rule, every section of the wire contributes to the magnetic field lines in the same direction within the loop. The magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, the magnetic field produced in circular coil having n turns is equal to n times the magnetic field produced in one turn. This is because the current in each circular turn has the same direction and the field due to each turn then just adds up. This is a comparison of the magnetic field lines around a straight conductor and a solenoid. In a circular loop, if the current is in the clockwise direction, then it is a south pole. And if the current is in the anti-clockwise direction, then it can be considered as the north pole. A coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. Comparing the magnetic field lines of a solenoid with that of a bar magnet, the pattern of the magnetic field lines around a current-carrying solenoid is similar to the pattern of the magnetic field lines around a bar magnet. One end of the solenoid behaves as a magnetic north pole while the other end behaves as a south pole. The field lines inside the solenoid are in the form of parallel straight lines, which indicates that the magnetic field is the same at all points inside the solenoid. That is, the magnetic field within the solenoid is uniform. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron and placed inside the coil. The magnet so formed is called as electromagnet. Electromagnets are used on the tracks of magnetic trains. It works on the principle of magnetic levitation. Large electromagnets are used in magnetic cranes to lift metallic objects, to separate metals from the garbage, and for various other purposes. Electromagnets are used in commercial motors, which makes the coil rotate. It is also used in doorbells and electric bells. When electric current flows through the coil, the electromagnet creates a magnetic field and pulls the magnetized arm towards it to strike the gong and hence produce sound.